Okay, we'll go ahead and get started. All right. So, what we've been going over so far, again, has been leading up to functions, and technically we haven't seen a real function yet. Though what we have been looking at has been very, very close and not far off. So, the things that we've been looking at might be in the form y is equal to something like 2x plus 7. And what we said last time is that this right here is the slope intercept form for a linear equation. So the slope being this number in front of x, the coefficient of x, and the y-intercept being this last number. Remember that the slope tells us how much each point on our line is changing from point to point, and then our y-intercept is where the graph of this function or this equation crosses the y-axis, so it would cross at positive 7. Now, there's really only one thing we need to do to make this a function, because right now we have two different variables. We have y and we have x. To make this a function, instead of having y, we will have f of x. Equals 2x plus 7. Okay, so what does this mean? Why are we using this strange f of x thing? So f of x defines a function. It is the name of this function. It's the name of the machine. So f being the type of function, or the name of the function, and x being the second part of that name, which actually tells us what this function is defined by. So what are we plugging in for this function? So in this case, we would be plugging in numbers for x. So the way that a function works is we can plug in a bunch of different types of numbers. And when we want to plug those in, we're going to be plugging them in for x. So for instance, if I wanted to plug in 2, what I would say is this is now f of 2. So again, it's still defined as being f, it's still named f. However, anywhere that we have an x, we're going to replace that with 2. So we have 2 times, we have an x here, so we'll replace that x with 2. Plus 7. Okay, so then we can go ahead and figure out what this is. So 2 times 2 is 4, and then 4 plus 7 is 11. So this would mean that f of 2 is 11. Okay, so simple. Again, not a whole lot of difference. It's just that when we are working with functions, we want them to be defined as being a function. So f of x. Now, does it have to be f? No, again, the letter there is just the name of our function. It can be h of x, it can be g of x, it can be k of x. You know, typically we use f, g, and h when we're talking about functions, but they can be any name. Again, it's just the name. So if we're working with multiple different functions, we might want to call them multiple different things so that we can keep them straight in our head. So let's look at some more functions here. Let me just pull that up for us. Okay, here's one that we're probably going to be familiar with. f of x equals 2x squared minus 7x plus 4. Okay, so we have a quadratic here. Yeah, quadratics can be functions. Any kind of equation can be a function. As long as it follows certain rules, though, and I'll get to that in a minute. We mentioned it last time, but I'll get to it in a minute again. So, same thing. This is just a machine that processes numbers. This is the input of the machine. We put whatever we want to put into the machine and process here. And then this part here is the actual working mechanics of the machine. It's what processes the number. This is the gear and the cogs and the engine and whatnot. And then once we get everything processed back here, it'll spit out a new number. So let's try plugging something in. Let's say -1. So f of x equals 2 x squared. Whoops, I meant to plug in a -1. So f of -1 equals 2 times -1 in for that x squared minus 7 times -1 plus 4. Okay. So again, all we need to do is just kind of go through the order of operations and process this number. So f of -1 first thing we can do here is, well, there's nothing to do in our parentheses, so exponent. -1 squared is going to give us just +1. So 2 times 1 minus 7 times -1 plus 4. Okay, now we can multiply things. So I've got 2 times 1 is 2. Then -7 times -1 is +7. So 2 plus 7 plus 4. Then add our f of -1 here. All right. And then let's see. We have 2 plus 7 plus 4. So that's going to be 13. So f of -1 equals 13. So we plugged in -1 for our input for this machine. The machine processed it and then gave us 13 as an output. Okay. So again, that's what functions really do. They process numbers. They take some kind of numbers in, process them a bit, and then spit something out. And so I'll pause for a second here for any questions. Okay, I'm not seeing any questions, so we'll move on. Let me give you this function. F of x equals 1 over 2x minus 6. Okay, so again, let's try to put a number into here. Let's try 3. So f of x equals 1 over, whoops, I meant to put in 3 in there. F of 3 equals 1 over 2 times 3 minus 6. Okay, so let's see what we get here. 2 times 3 is 6. 6 minus 6 is 0. Ooh, we have a problem. So if we go through the order of operations here, again, 2 times 3 is 6. 6 minus 6 is 0. That means we have 1 over 0. So f of 3 is 1 over 0. And as we have learned in the past, that's not okay. We cannot have 0 in the bottom of a fraction like this because it means that we're dividing by 0. And in algebra, that's a no-no. That means that f of 3 is undefined. So this does not work. We cannot plug in 3 for our function here. So this is getting into the idea of a domain. Domain is another word for all of the things that x can be or cannot be. So we would say that the domain here for x in this function, the things that x can be, the rules for that would be x cannot be equal to 3. Okay, well, how do we figure that out? How do we know what we can't plug in here? How do we know what is going to be excluded from the values that we can plug in for x? It's actually very simple. Anytime that you have a function like this, where you have a fraction, take whatever's on the bottom of the fraction and say this thing, in this case 2x minus 6, cannot be equal to 0. Basically what we're saying here is the stuff on the bottom here, we don't want it to be 0, because if we have a 0 on the bottom of this fraction, it breaks. We get undefined. We get something divided by 0, and that doesn't work. So again, whatever's on the bottom here, we don't want it to be 0. So we'll literally say 2x minus 6 can't be equal to 0. And then we can solve that. So I would move 6 to the other side by adding it. Cancels there. Now we have 2x is not equal to 6. Then we need to divide the 2 off of x. And that gives us just x over here is not equal to, well, 6 divided by 2 is 3. And so there's our domain. Okay. So, again, if we want to make sure that we know what we can and cannot plug in for x into our functions, we need to find the domain for that function first. And when we have fractions, that means whatever's on the bottom of that fraction, the denominator, in other words, must not be equal to 0. So we take whatever's on the bottom, again, in this case it was 2x minus 6, say that it is not equal to 0, and then solve. And we'll get our rule for our domain. Okay, so let's try another one. Basically the same idea. This time I'm going to have h of x, just because we haven't seen that yet. Again, just because it's h of x doesn't mean anything different's going on. It's just the name. 2x over x plus 2. Okay. So I want to find the domain for this function. Well, it has 2x over x plus 2. Do I need to do anything to the top? No. Even though I have x up there in the top, it doesn't matter. I can plug in anything I want for x in the top here, and it will not affect the bottom. You know? Only the top part is going to be excluded from this. The bottom part's where we start having problems. There's a certain number that I can plug into the bottom here to make this bottom part 0. So I need to say, take the bottom part, in this case x plus 2, and say that that cannot be equal to 0. And this one's pretty easy to solve. All I got to do is take 2 to the other side. So subtract 2. That gives us x is not equal to -2. There's our domain. Again, we don't need to worry about solving anything for the top part, because the top part, we're not ever going to get divided by 0 or anything crazy like that in the top. It's just the bottom that's going to give us something weird. And that weird thing is we can't have this thing equal to 0. Okay. So we have two different examples here for our domain when we have a fraction. And again, this is any time that we have a fraction for our function. If you have a fraction somewhere in your function, take the denominator and say it's not equal to 0. So again, I'll pause for a second here to allow us for any questions. Okay, let's move on. So are there any other places that we might have domain problems besides fractions. Yeah. One that comes to my mind is if we have something like g of x. Again, doesn't matter that it's g, that's just its name. Equal to, let's say, the square root. That's an ugly looking square root. Keep trying. That's better. If we have square root of, let's say, x plus 5. Okay, so we've seen in the past that square roots can do interesting things if they have a negative underneath them. And we've said, all right, we can tackle that. It's just if there's a negative number underneath that square root, then it's going to be I. The problem with that, though, is if we think about our graphs, our grids, there's no I values on there. We can't graph those. Those actually are not things that are allowed in functions for this. So if we get a negative underneath this square root, it's going to give us an imaginary number, and that's actually not something that we want in our function. We don't want to deal with imaginary numbers in our function. So we're going to have to exclude those. We're going to have to say that our domain can't give us any kind of imaginary number. So how do we say that here? What do we do for this to find the domain then? Well, we have to say that x plus 5, whatever's underneath the square root, again x plus 5, has to be bigger than or equal to 0. Because anything that is bigger than or equal to 0 is not going to be negative. 0 is fine. Square root of 0 is 0. Anything past that, though, going towards the negatives is not going to work. Any negative number underneath the square root is going to give us some I value. So we solve this by subtracting 5. And that means that x must be greater than or equal to negative 5. So anything that is bigger than negative 5 is going to work, or equal to negative 5. That's fine too. So let's try that out a little bit. Let's try a number that's within our domain, something bigger than or equal to negative 5. So something like negative 1. So g of negative 1 equals the square root of negative 1, and for that x, plus 5. So what do we get here? Negative 1 plus 5, that's 4. So g of negative 1 equals the square root of 4. And what is the square root of 4? That means that g of negative 1 is plus or minus 2. So we don't get an I value. Everything's fine. We don't have to worry about any weird values coming out of this because we used a number that is within our domain. It fits the rules. And again, that rule is that x must be bigger than or equal to negative 5. So let's try something that isn't in our domain. Something like negative 6. So g of negative 6, again, this is not in our domain, so it's not going to work. But let's just see what that looks like when it doesn't work. G of negative 6 is the square root of negative 6 plus 5. What happened there? So negative 6 plus 5, that's going to give us negative 1. So g of negative 6 equals the square root of negative 1. And that's where we get problems. We don't want negative numbers underneath our square root because it gives us those imaginary values, and we don't want that. So this is undefined technically. We know how to deal with these, yes, but it's not going to be something that we can put on our graph of our function. It's not within what we want for our function. We want real numbers when we get our function to work. Okay? So when we get these non-real numbers, then we have problems. So again, this is what it looks like when we use numbers that are not within our domain. Okay, so let's try another one of these. F of x is equal to 3 times the square root. It's so hard to make square roots on this tablet. Of negative 2x plus 4. Okay. So again, if we want to find the domain of this, what we need to do is take only what is underneath the root and say that it must be greater than or equal to 0. The 3 doesn't matter. We don't need to worry about that 3. It's outside of this square root. It's outside of the thing that's giving us problems. So it's only that negative 2x plus 4 that's going to give us problems eventually. So again, we need to take that thing, negative 2x plus 4, and say that it must be greater than or equal to 0. Again, the reason we say greater than or equal to 0 is because anything that is bigger than or equal to 0 is not negative, and we don't want negative numbers. So we need to solve this. Take 4 to the other side. Cancels there. We now have negative 2x is greater than or equal to negative 4. And now we need to divide the negative 2 off of x, and remember that this is going to do something. Because we divided by a negative on both sides, this inequality is going to flip. So now we have x must be less than or equal to, let's see, negative 4 divided by negative 2, it's positive 2. So x must be less than or equal to 2. Okay. So again, let's try things out. Let's just make sure this domain makes sense. So we'll choose something that is less than 2. Let's try 1. So f of x, f of, let's say 1, equals 3 times the square root, square root of 1 times negative 2 plus 4. So negative 2 times 1 is negative 2. Negative 2 plus 4 is 2. So we get f of 1 is 3 square roots of 2. And that's fine. We don't have one of these weird I values. This is a perfectly real number. So, yeah, it works. So now let's try something outside of our domain, something that is bigger than 2. So, 3. All right. So f of 3 equals 3 times the square root of negative 2 times 3 plus 4 Okay, so negative 2 times 3, that's negative 6. Negative 6 plus 4, that's negative 2. So now we have f of 3 equals 3 times the square root of negative 2. And the square root of negative 2 is going to give us an I value. That's not what we want. Again, we want to get rid of anything that might give us an I value. So again, yeah, this is outside of our domain. So this makes sense. Our domain that we found works. Okay, so I will pause again for any questions we may have. Okay, so I don't see any questions. And surprisingly, yeah, we've actually gotten through what I wanted to get through today. So I'll leave us off with a little bit of a bonus. Okay. So we can find what we want for the domain of x. We can find the numbers that we want for x. And, whatever rule we have for what x can't be. What about y? We have 2 axes on our graph. We know what we can plug in for x. What about things for y? Can we define what y can be? Yes, absolutely we can. Now that does get into something a little bit different though, and I'm going to show you the little bit different part before I show you how to find the range, which range is the same thing as domain just for y instead of x. So, to find that, we're going to need to be able to do inverse functions. So before we leave, I'll show you one inverse. So what an inverse function is think about, again, the machine idea. If we have a machine, f of x, and its parts say 2x plus 3, then this will process numbers by first multiplying it by 2 and then adding 3. And it will give us a new number out. An inverse function does the opposite. An inverse function will take these parts and basically like run it in reverse. So if we want to find an inverse function, which is actually very useful, and I'll show you that Monday, the first thing we do is we need to say, all right, let's put this back into a generic form. Y equals 2x plus 3. And the reason we want to do that is because an inverse function basically switches x and y. So we're literally going to do that. We're going to switch x and y. If you look at the graph of an inverse function, you can actually see how it switches all the points for y and all the points for x. It literally switches their positions, because what we're doing, like we said, is running this thing in reverse. Our x's are going to become our y's, and our y's are going to become our x's. So we're going to do that in order to find our inverse function. We're going to switch x's and y's. Now we need to solve for y. We need to put it back into this type of form by solving for y. So the first thing we do is we subtract 3. Cancels it out here, brings it over to this side, so x minus 3 equals 2y. And now we need to get the 2 off of y, so we will divide that off. And so once we divide that off, we now have x minus 3 divided by 2 equals y. So y is by itself. And I'll rewrite it up here. Y equals x minus 3 over 2. And now we need to put this into a form that says that it is an inverse function of this one. So the way that we show that this is an inverse of this one is we change this back to f of x, but we add a little thing here that says -1, power -1. Remember, anything that we take to the power of -1 makes that an inverse of the original number. So f to the -1 of x equals x minus 3 over 2. So this is the inverse function of this. These do the opposite. So like I said before, when we plug a number into this original function, the first thing it does is divide by 2 and then add 3. In our inverse function, again the opposite of this function, what happens is we subtract 3 and then divide by 2. Literally the opposite order and the opposite operations. So here we're multiplying by 2, then adding 3. Here, opposite of adding 3 is subtracting 3. Opposite of multiplying by 2 is dividing by 2. So again, it does the opposite. So like I said before, inverse functions are going to become very important for us when we're trying to find range, the numbers that y can be. But I will save that for Monday. So that actually I'll stop for any questions we might have before we end today. So just let me know if you have any questions. Okay, I don't see any questions. So again, Monday we will be getting into more of these inverse functions and how they help us out understanding our original function. But that is all for today. I hope you have a good weekend. Continue staying safe, and I will see you later. So, have a good one.